All right, we're back to the chalkboard, which is nice. I like it a lot more than editing PDFs, but trying to be consistent. So let's do number 4 in the homework assignment. For the following exercises, sketch the situation, if necessary, and use related rates to solve for the quantities. This first one might be kind of hard to sketch, but let's kind of look at it. If 2 electrical resistors are connected in parallel, the total resistance, measured in ohms, denoted by the Greek capital letter omega, is given by the equation 1 over R. So this time it gives us the equation. That's going to be nice. It's going to be 1 over R equals 1 over R1 plus 1 over R2. That shows the total resistance given each of the individual resistors, just adding up the reciprocals for everything. If R1 is increasing at a rate of 0.5 ohms per minute, R1 is increasing at a rate of 0.5 ohms per minute, and R2 decreases. So if it's decreasing, then that means the rate of change is negative. R2 is decreasing at a rate of 1.1 ohms per minute. The resistance is going down here. At what rate does the total resistance change? That's what it's asking us. What rate does the total resistance, dRdt, change over time when R1 is 20 ohms? And again, ohms, that omega, that's the unit, not part of the number. And R2 is 50 ohms. So this one's a little tricky to sketch if you're better with electrical engineering and stuff, then you could probably draw a good sketch. But for me, I don't see a picture really helping me out that much. And besides, usually the pictures are just a good way of organizing information, but they already give us the equation here, which makes it a little less necessary. One thing I would do is I would rewrite this equation because we're going to be taking the derivative. And it's usually a lot easier to take the derivative when you write things with negative exponents. We need to take the derivative of both sides of this equation with respect to time. And we're going to have to use the chain rule. This is implicit differentiation. So, power rule, bring down that exponent, subtract 1 from the exponent. The inside stays the same, and multiply by the derivative of the inside. And in fact, that's going to be the derivative of all of these, right? This is going to be negative R1 to the negative 2 times dR1 dt. And then negative, oh, I do not have enough room for this. Here, we'll just draw really tiny. Negative R2 to the negative 2 times dR2 dt. And now we just plug things in and see what happens. So we have to start by plugging in what is R. And we don't know, but we can find it, right? Specifically, we're looking at this moment in time. If R1 is 20 and R2 is 50, we know what R is. We can just use the formula. Right, 1 over R is 1 over R1 plus 1 over R2. Find a common denominator. Cross multiply. Couple of ways of doing that. I think multiplying both sides by 100R is another way of doing it. That's multiplying both sides of this equation by the LCD. If you multiply both sides by 100R, you're going to get 100 equals 5R plus 2R, or 107R. So R, I realize this is by my head, is 100 over 7. Which is about 14. So we're going to have negative 1 over 14 squared. Sorry, not 14. 100 over 7 to the negative. I'll try not to skip steps here. Times dr dt, which is what we want to know, equals negative r1, which is 20, times dr1 dt, which is 0.5, minus r2, which is 50, to the negative 2 times dr2 dt, which is negative 1.1. The negatives are going to cancel here. Now it's just a little cleanup and solving this equation. So these all have negative exponents. These are all reciprocals, right? This is 7 over 100 squared. Negative exponent means reciprocal. Second one is going to be negative 1 over 20 squared. And there's also a 2. And then again, this becomes a positive 1.1 over 50 squared, like so. Gosh, there really are a lot of ways to make silly errors in this problem. Let's clean things up a little bit before we go on any more. Negative 49 over 10,000 dr dt equals, that becomes 400, that becomes 800, plus 1.1 over 2,500. And now we're just going to multiply both sides by the reciprocal and use a calculator. Negative 10,000 over 49 times this whole thing. And use a calculator to get our approximate answer. So if we do that, we get negative 10,000 divided by 49, right? That's what we found. And then 1.1 over 2,500 minus 1 over 800 is about 0.1653. And the units are going to be in the units of R, which is in ohms, per T, which is in minutes. So at these specific resistances, resistance of the first is 20 ohms, second's 50 ohms. First is increasing by half an ohm every minute. Resistance of the second is decreasing by 1.1 ohms per minute. The total resistance is still growing a little bit by 0.1653 ohms every minute. All right, that's how you can approach a problem that looks a bit different. I tried to choose this one because it is a bit different looking than the problems that we did in the regular lecture ones. Let's do number, I'm getting lost on my screens. Number 42. Baseball. Sides of 90 feet in the baseball diamond. So a batter is hitting a ball towards third base at 75 feet per second. Let's copy this down. Okay. We have our diamond, third base is on the left. Everything is 90 by 90 by 90 by 90. And specifically, it's hitting the ball 75 feet per second in this direction. And runs towards first base at a rate of 24 feet per second. At what rate does the distance between the ball and the batter change when 2 seconds have passed? We're looking at this distance between these two things. Okay, so we can make a smaller version of this problem. All right, 2 seconds passing. Wait, what? All right, no, it's fine. So 2 seconds passing, how is the ball gone? 75 feet every second. So in 2 seconds, it's gone 150 feet. This is our ball. 2 seconds passing, how fast has the batter run? 48 feet. All right. This is the person. And we're looking for the distance between them. Let's call that Z. And how is that changing? Is a baseball diamond 90-degree angles? Yes, it is. Great. That's not actually true, is it? We're just assuming it for the simplicity of the problem. Are baseball diamonds actually 90 degrees? Oh, it kind of does look like it, huh? I don't like baseball, guys. I don't know anything about baseball. All right, maybe it is 90 degrees. Okay. So let's, you can call these variables whatever you want. I'm going to like tilt my head a little bit and call this X and call this Y. It doesn't really matter. But again, this is going to be the Pythagorean theorem. So we know that X is 48 at this moment in time. Y is 150. Z, we could also find that out, right? 48 squared plus 150 squared equals Z squared. So Z is going to be the square root of that. 48 and 150. Z is about 157.4929. Approximately. Also in feet, we know that X is increasing by 24 feet every second. We know Y is increasing. We're assuming it's not slowing down over time at 75 feet per second. And we want to find how Z is changing over time. So step 3 was to write the formula that relates all these quantities, X squared plus Y squared equals Z squared. And now we use implicit differentiation. That's step 4, just like before, 2x dx dt plus 2y dy dt equals 2z dz dt. And we plug in only at the very end. If we plugged in earlier, we just get something equals 0. Not very useful. Just like when we're calculating derivatives in general, you can't plug in until you know the derivative function. That's the same idea here. Want. I'm not changing that. So 2 times x, which is 48, times dx dt, which is 24, plus 2 times y, which is 150, times dy dt, which is 75, equals 2 times z, which is about 157.4929, times dz dt, which we want to find. You can clean things up and solve, but you should get, at the end of the day, that it's 2 times 48 times 24 plus 2 times 150 times 75 all over 2 times our answer, 157.4929. About 14.46 feet every second is how far these the ball and the person, the batter, are moving away from each other at this point. All right. 2 seconds is pretty... I don't know anything about baseball. All right. And that one is a little better than the last one. Let me know if you have any questions, and have a good day.